Hello everyone. In today's lecture video, we will continue our discussion in chapter 1 part 3, which is entitled Computer Arithmetic. So before I am going to continue, let me go to this slide first. Let's say here, this is our last topic. Our last topic is all about this one. Okay, so we have how to write a real number in a base 10 form. This is this one, and I corrected also this k here, the second summation, which before I write it as k is equal to 0. Okay, so this is the integer part and this is the fractional part, and also this is the general form on how to write a beta system numbers in beta system. Okay, so this is the more general form, and as you have noticed, if b is greater than 10, or simply b is equal to 10, then we have to be careful on how to put a separator on those numbers. Okay, so maybe you can replace it by a letter. Let's see that one in our topic, which will be discussed later when the case beta is equal to 16, which is what we call the hexadecimal number. And also, as suggested, it is advisable to when we are going to convert a real number to any system, it is advisable to separately do the calculation in the integer part first, and then after that we have the fractional part. Okay, so last meeting we do this one. After writing it in this form, we write it in the nested form. So this is the nested form. I discussed on how to write this notation, and we also discussed this one. This procedure is we convert the given into its general form, and then after that we replace each number here in the system that we are going to arrive. Example, if we are going to ask the base, we are going to convert this in a base 8 or base 2 numbers, then we have to convert these factors to that number, with the given number, and then do the calculation. And also we discuss another procedure which is much easier by using the division algorithm. So all you have to do is to divide this number repeatedly by the base that you are that were asked in the problem, and then after that write it in collect those remainders, then that's your answer. You will start at the top to bottom, and then this one is a what if we write it in the presentation. I guess most of you got the correct answer, and this one also, and this is our topic now. Okay, conversion of the fractional parts. Okay, so before we proceed to the conversion of the fractional part, let me give you an illustration which is the same as the one we did before, like this form. Okay, the given, we should write it in just this form first, and then replace these numbers by what they call this one, by the beta number that you are going to get. Okay, so let me have this illustration first. Skip. Let me open my whiteboard. Okay, so last meeting. Okay, not this one. That's okay. Let's try this one here. Okay, so let's try to convert this number using the previous method. Okay, we okay, illustration. So this convert let's say I forgot. Let's try to convert, where are you, 0.237 0.237 0.237 in base 10 to binary form, binary number. Sorry. Okay, so let's have the solution. So just like before. Okay, so we have 2 times 10, 2 times 10 to the negative 1 plus 3 times 10 to the negative 2 plus 7 times 10 to the negative 3. Okay, so this is equivalent to 2 over 10. Sorry, let me over 10 plus 3 over 10 squared plus 7 over 10 cubed. Okay, so we write this one in listed form first. Okay, so let's factor out 1 over 10. Factor out 1 over 10, and then we have 2 plus 1 over 10 times 3 plus 1 over 10 times 7. Okay, we have this one. Okay, so after this we convert the number to example number 10, number 1, number 2, number 10, 1, 2, 3, 7 to binary. Okay, so this is 1 over, we know this already, plus 2 is 0, 1, 0, plus this is 1, 0, 1, 0, and then 3 is 011 base 2 plus 1 over 10102, and then 7 is 1 1. Okay, let's move this one here. Okay, that one. So as you can see, dividing in binary arithmetic is not straightforward. So what we will do here is we will find another method on how to convert a given decimal number to a binary or any base. Okay, so but if you insist, you can search in the web, the internet, and then try to study on your own on how to perform the division in binary arithmetic. Okay, so well, anyway, let's proceed. Let's have another method. So this one here, so this is the method on how to convert a given number to its beta representation. So suppose that you are given a real number, which is of course a fraction or a decimal, because as you can see here, it is between 0 and 1. So this is very obvious from this notation. We use our digits. We have here C sub k as our notation for the digit. So this is the tens, hundreds, thousands, and so on and so forth. And then as you can see, if we are going to multiply by beta both sides of this number, we will get in this form. Okay, so it will move one place here. Okay, so because it is necessary to shift the radix only when multiplying, let's say, let's hide this one, by multiplying, where are you, by base beta. Thus the unknown digit C1 can be described as the integer part of Bx. So for now, after multiplying by beta, your C1 here is what we call the integer part, and C2, C3, C4 is the fractional part. For beta x, beta x is denoted as your integer part, while C2, C3, C4 is your fractional part and is denoted by this symbol. Okay, so after that, continue the process of multiplication and you will arrive in this form. Okay, and after that, it says here in this algorithm the arithmetic is carried out in the decimal system. So let's try to perform this one here in example 11 using this method that I present to you a while ago. So let's try to solve this one. This is, don't forget that this is base 10. Okay, so let's try to solve this one using the previous discussion. Okay, let's say solution. Let's try another color here. Solution. Our given is 0.237. So the algorithm consists in repeatedly multiplying by 2 and removing the integer parts. So here is the work. Okay, we have 0 point let me recall it again, 237, 0.237. Let's say 237. We multiply this one by 2. So what do we get? So I have a calculator here. 0.237 times 2. So we have 0.474. 474. Okay, before that, let me use a color here. Let's say red one. This is 0, and then we have another 0.474. 474. Okay, so the red one is your, let's try this color here, C sub 1. Okay, that red color. Okay, and then let's multiply again by 2. So multiply by 2 times 2. So in my calculator we have this color red, 0.948. Okay, so we multiply again by 2, and this is C sub 2. So let me put a box here somewhere, that one. Okay, color green, and let's move upward. Okay, 0.98 times 2 again is 1. This is 1.896. Sorry, red color, 1.896. Make it clear somewhere here. So this is C sub 3. That one. We multiply again by 2. So where does it end? If it will end at 0, so you will stop, but if not, then perform at least maybe 10 multiplication, so that it will be enough to represent the given to its binary form. 1.896 times 2 is 3.792. So as you can see here, the product, let's have this color yellow. Let's have a bubble thought here. The product is 1 3.792. Okay, so since we are performing in binary, the digit 3 is equivalent to 1. Okay, so this is 1.792. Okay, and then multiply again by 2. 1.792 times 2 is, again, this is 3.584. So 3 here is replaced by 1. So we have 1.584. Okay, so continue the process. We have C sub 4 here, C sub 5 here. So this one times 2, we have 1.584 times 2. We have, again, this is more than, this is 3.168. so replace again is 1 by 1. So all those odd numbers is replaced by 1, and all those even is replaced by 0 in binary. So 168. Okay, sorry for this one here. Let's have this red color. This is 1. Okay, so let's have here C sub 6. Okay, so etc. So if you continue the process, we have an infinite multiplication. So therefore we write, sorry, let's have color green. Thus we have 0.237 in base 10 is equal to, let's say, 0 0 1 1 1 0. That's 0 0 1 1. How many 4 ones? Okay, you have dot in base 2. Okay, so this is the answer. So that's how you are going to convert a number, a given, to its beta form. Okay, this will also work for any base. Okay, remember that in our discussion, right, open board, let's where are you? Remember that our beta is in general form. So as you can see here, we have our beta is in general form, so you can replace any beta from 2 to and so on. Okay, so that will work for any beta. Okay, so let's proceed we have here. So okay, so for the next topic we have base conversion from 10 to 8 or to 2. So this is much easier if you follow this method. So most computers use the binary system base 2 for their internal representation of numbers. When numbers are converted between decimal and binary form by hand, it is convenient to use octal representation as the intermediate step. So meaning to say, in the second sentence, it says that if you want to convert from decimal to binary, so you must convert it first to the octal representation, and then you will use this table. It says here in the octal system, the base 8, the base is 8, and of course these digits 8 and 9 are not used, because in the octal system we have only the digits 0, 1, 2, 3 up to 7. So conversion between octal and decimal, of course, proceed according to the principles already stated. Conversion between octal and binary is especially simple. So what you will do is you are going to group the binary digits into three binary digits, and then use this table. So for example, this one here, if you are going to convert this into uh, octal, and then after that in binary. Okay, so let's have an illustration here. Okay, so divide, use this method first. So it says here in the second sentence that in order to convert to a binary, you have the it is convenient to write it in octal representation first as an intermediate step. So this one here, convert this using this method. Okay, for the fractional part, and then for the integer part is using division algorithm. Okay, so let's try solving this one here. Okay, so let's try new page here. Okay, so our number is, where are you, given solution, our given is, let me recall, we have 5267.5 5354 6857 6857. This is in base 10. Okay, so our question is convert in octal and then in binary. Okay, so we convert. So what we'll do here is we convert the original number, decimal number, convert decimal number first to octal, and then to binary. Okay, let's convert the integer part first. For the integer part, uh, we repeatedly divide by 8. So as you can see here, 5, 2, 6, 7. Okay, 5, let's have this color. 5, 2, 6, 7. 5, 2, 6, 7. Okay, so let's divide this one by 8. So our quotient is 5, 2, 6, 7. I have here my calculator. Divided by 8 is, we have 6, 6, 5, 8. 6, 5, 8. 6, 5, 8. And our remainder is 6, 5, 8 times 8 minus 5, 2, 6, 7. Of course, you have a negative number here. So, write the positive one. So, we have 3. Okay, the remainder is 3. Okay, and then divide again by 8. Just like before. So, 6, 5, 8 divided by 8. So, we have here 82. 82. 82 times 8 minus 658. So we have 2 here, the remainder is 2. Okay, and then proceed again, divide by 8. 82 divided by 8, so we have 10 here. And of course our remainder is very obvious, we have 2. And then divide by 8 again, so we have 1 here, and the remainder is, of course, is 2. Oh, no, 2. Okay, 2, the remainder is 2. 8 times 1. Okay, and then lastly, divided by 8, we have quotient is 0. Am I right? We have 1, 8, 7, 1. Okay, C sub 4. The remainder is sorry, we have 322, 82. Let me erase this one first. Okay, that one. Remainder is 1. Okay, so thus we have 5, 2, 6, 7 in base 8, 5, 2 in base 10. Point is equivalent to, this is 1, 2, 3, no, 1, 2, 2. Sorry, this is 1, 2, 2, 2, 3 point in base 8, And then notice that if we use the table, we have 1 2. 1 is 0 0 1. Okay, replace the digit by this table. 1 2 1 0 1 0 0 1. Let's move this one upward. So we have, let's try this color, let's say green. For 1, sorry, it's the one here. Let's have green. We have, for 1 we have 0 0 1 0 0 1, and then for 2 is 0 1 0. Let's have this color, 0 1 0 0 1 0, and then we have 3 2's, 0 1 0. We have 3 here, 0 1 1. Let's have this color, let's say yellow or green or red, black. 3 is 0 1 1 0 1 1. Point, okay, in base 2. And notice that this is our a sub 0. Okay, a sub 0, a sub 1, a sub 2, and so on and so forth. So meaning to say, we can delete our 0 here because 0 times a number is 0. So we can write it in this form. Let's say this is the final 1 0 1 0 0 1 0. How many? Okay, 0 1 0 0 1 1. Point this one here. Okay, so for the fractional part, let's move somewhere here. For the fractional part, so just like the method before, we repeatedly multiply by 8. So let me go back to this one here, 0.534 0.534 5354, sorry, that's 5354 5354 6857 6857. We multiply this by 8 repeatedly. Notice that our the digit must be, okay, the integer part after multiplication must be between 0 to 7. So 0.5354 6857 times 8, using my calculator, we have 4.2837256. multiply by 8 again, times 8. It's what we have done before. This is C sub, this is our C sub 1. Okay, so multiply again by 8 is 34. Okay, so let's have a bubble thought here. Bubble thought. So the answer is 34.2698048. 2698048. So the integer part here, if you want to convert it to an octal number, so what is 34 in the octal number? So we have, all you have to do is to subtract it until it will become a number between 0 to 7. So this is 34 is 2 in octal, so this is 2.2698048. Multiply by 8 again, so this is 1 here. This is our C sub 1, C sub 2. Okay, so continue the process. Multiply by 2, 2.2698048 times 8. So we have 18. So this is, let's try this color. A bubble thought here, we have 18.158434 using my calculator. 1584384. And this in octal, so we have 18 minus 8 minus 8. So again, this is 2. We have 2.1584384. Multiply by 8 again. So this is our C sub 3. So 2.1584384 times 8. We have 17. So maybe you can extend it until maybe up to 10 multiplication. So you will have a good estimate. 2675072. So 17 is what number in octal? 17 minus 8 minus 8 is 1. Sorry. So this is 1.2675072. So 1.2675072 times 8 again is 10. Times 8, we have 10 point, or shall I say 10 is greater than 8. So let me put a bubble thought here. we have 10.1400 576, so 10 is 2. We have 2.1400 576. This is C sub 5. Let's have a last one times 8. We have 2.1400 576 times 8. We have 17 again. 17. Sorry, maybe I made a mistake here, I don't know. We have 17.1204 608. So this is C sub 6. Okay, so etc. We continue the process. So what we have here, our conclusion, so that 0 point, okay, where are you, 5354 68, what's that one, 6857. In base 10, this is 0 point that we have here, 42212 42212 that we have in base 8. And in what we call this one, in binary, we have 4 is replaced by 100. Okay, 100. 2 is 010 010 010. 1 is 001, and then 2 is 010. That. So this is in base 2. So let's combine. Finally, we have we obtain the result. This is where are you, 5267 5267.5354 6857. In base 10, this is in decimal, we have 101 010. We have 1 010 010 010, 3 2's, and then 011. We have point, no, not this one, 011 point, and let's use this one here. Okay, so we have 1 0 0 0 1 0 0 1 0 0 0 1 0 1 0 dot 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 in base 2. So this is our final answer. Okay, so before we proceed, our next discussion is let's hide this one first. Okay, we solve example 12. Sorry. Okay, we will discuss base 16, how to do this one. Okay, so okay, finally, when we are going to convert a hexadecimal number, we will use this method. What we will do here is that just like what I mentioned before in the previous discussion, if the digit is greater than 9, especially when we are given a digit which is 10, 11, 12, 13, and so on and so forth, we will replace it with a symbol or a letter. The reason is as what I have said before, if 10 and 9, for example, let me illustrate it here. For example, if sorry for that one, let's have another page here. If you have let's say in a hexadecimal number, if you have 1 8 6 1 2 9, for example, that one, this is in base 10. No, not that one, in base 16, for example. This is in base 16. Notice that for example here, this one here, if we have this notation, this one, okay, that those numbers in red, it can be interpreted as 1 and 12, 1 comma 12, or it can be interpreted as 11 comma 2. Okay, so therefore it is necessary to what do you call this one, it is necessary to replace number 10, 11, 12 up to 15 into a letter, okay, so that you will not be confused in solving the given problem. But anyway, if you are going to convert a binary to hexadecimal or hexadecimal to binary, you will use this table. Okay, so for example, but before we are going to the example, let me read to you this sentence here. It says, conversion between binary numbers and hexadecimal numbers is particularly easy. We need only regroup the binary digits from groups of 3 to groups of 4. Okay, so the reason for this is, notice in the previous slide, this one here in Octal, all you have to do is to group into 3. If you are given in binary, you will group it into 3, But in the hexadecimal, you will group it into 4. Okay, group it into 4. So for example, this one here, uh, let me open my open board here. Let's say, let's move this one. No, let's erase this one. Okay, let's erase this, and let's try to solve this one here, the first 0 1. How many? 0 1 0 1 0 1. Okay, we have solution. We have 0 1 0 1 0 1, and then we have 0 1 0 0 1. We have 1 1 0 1 1 1 0 1, 0 1 0 1 0 1 1 1 0 1 0 1 1 0 0 1 1 0 1. Okay, this is in base 2. So if you are going to convert it to a hexadecimal number, this one here, okay, so you have to group it into 4. Let's try this color. Let's say the red one. We have 0 1 0 1, and let's have this let's say yellow. We have 0 1 here, 0 1 0 1. We have 0 1 1 1. Okay, 0 1 1 1, 0 1 0 1 0 1 1 1, and then I guess 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So we have to start here. I'm sorry, from the right. I guess we have to move back. Okay, move back. Okay, we will start here. Okay, this is C sub 0 or A sub 0. Okay, okay. So let's group it like this. First is we have 1 1 0 1. Let's say 1 1 0 1, and then 0 1 0 1. And 0 1 0 1, 0 1 0 1, and then let's see, we put a mark here. That is 1 0 1 0 this one. Okay, and then this one also. Okay, so meaning we have this green one, 1 1 0 1, and then lastly we have color blue, or let's say color black. We have 0 1 0. Okay, and we have to enclose this one. Remember that if the red the black color, this one here, before 0, this will you can put 0 here. It doesn't matter because 0 times a number is 0. Okay, so you can replace 0 somewhere before. Okay, so this is 0 0 1 0. Okay, so anyway, let's use base 2. So what is 0 0 1 0? Let's look at the table. We have 0 0 0 1 0. We are in 0 0 1 0 0 1 0. 0010. So we have 2 here, 0010. The first is 2, and then the green one here, 1011. 1011 is B. 1011. This is 11. Okay. B. We have B here, letter B. And then 1010 is 10A. So this is A. And 1101 is B. Okay. Okay, so we are done. Okay. And the second question is this one here. Okay, so let's convert the second question. So what is that? 4 ones and then 0101. 4 ones. 1, 2, 3, 4, 0101. Okay, 4 1 0101. 0101. And then 3 ones and 0. 3 ones. 3 ones. 1, 2, 3, and 0. 3 ones and 0. And then 0, 1, 0. We have 0, 1, 0. That 1, 1, 0, 0. We have 1, 1, 0, 0. And then 1, 1, 0, 0. And then 1, 0, 0, 1. 1, 0, 0, 1. And then 1, 1, 0, 1, 0, 0, 1. And then 3 ones and 0. 3 ones and 0. In base 2. Okay, let's group this one. So from the integer part, we will group it like that, and for the fractional part, we will group this one. Okay, so let's try to group it. So first is group this one, and then this one here, and then here. Okay, we have 3 ones here. So we will group this as 1, 1, 1. Another color, we have 1, 0, 1, 0, 1, 0, 1, 0. And then let's try the color green. We have 1, 1, 1, 1, 1, 1, 1. And then let's try this yellow here. We have 0, 0, 1, 0. Point. Let's move it somewhere here. Okay, so we will group it this way. This one here, then this one, and then finally we have this yellow. Okay, so okay, it's a perfect number. We can group it into 4. Anyway, we can try it this method. We have 1, 1, 0, 0, and then 1, 0, 0, 1, and then finally we have 1, 1, 1, 0 in base 2. Okay, so finally we can replace it. Let's say color green. Okay, for this part here, this one, 0, 0, 1, 0. Let's what's that one? 0, 0, 1, 0. 0, 0, 1, 0 is 2. We have 2. Maybe we can start here. 0, 0, 0, 1, 1. 0, 1, 1, where are you? This is 7. Okay, so 7 1010 is this one, A, and then 111 is F. 0010 is 2. Point 1101, the block 1. 1101 is T. 1100, sorry. 1100, 11 C. We have C. 1001. 1001 is 9. And then 131 and 0. 31 and 0 is E. So this is in base 16. I'm sorry, I made a mistake here. This is base 16. Sorry, this is base 16. Base 16. Base 16 here. Okay. So I guess we are done on how to convert a base 10 into a base 16 to base 2. Okay, so if you are given a base 10, so first is you have to convert it to octal and then to this method here. Octal, go to octal if you are given a base 10. Here you are base 10, go to 8 and then go to 2 and then go to 16 if you are going to convert from decimal to hexadecimal. Okay, that's the most efficient way. Okay, so but if you are going to convert from hexa to DC, so you will use the general form. Okay, this one here, this one, where are you? That's this one here. You will use this method. Okay, converting from octa to DC, or maybe from binary to DC, you can use this one, or you can use the table. Okay, that would be much easier. Okay, for our next topic, we will be discussing the floating point representation of real numbers in a computer. Okay, so God bless everyone. Thank you for taking time to watch this lecture video. Okay.